So I am sort of, my background is in networking, but I've sort of been sort of moving into quantum networks. I think generally I'm interested in decision making, particularly in networks. Quantum networks have lots of interesting decisions that are just slightly different from the networking. And so it's pretty interesting to think about. So how familiar are people with networks? Okay. Perfect. So my plan is just talk a little bit about networks, quantum networks, what we mean by that, and then talk about quantum key distribution in a network, and then if we make it, talk about some practical improvements in those networks that I did with some folks at UConn. Okay. Okay. So what is a quantum network? So the first quiz, well, not quiz, is what is the point of a network? Okay, so why do we use networks? You're probably pretty familiar with this. I took a little snapshot of Middletown, where Wesleyan University is. You have Alice Bob. So networks share resources, right? We're conveying information, and the information that's being conveyed in those networks, zeros and ones, right? Bits. The connectivity of the network. So if a link fails here, you might still have another path to your destination, right? Okay. And also, even if a link hasn't failed, you might have a lot of congestion in the network, and that will also allow you to take different paths. Okay, so it provides a little bit of robustness, not just have a single path between one and another end host. And of course, you might have multiple users all sharing the same resources. So a quantum network is actually trying to do a lot of the same things. So you may want to be sharing resources to scale the computational power of those resources. So if you think about, like, have you guys used things like Google Cloud, ECT? Okay, exactly. So you're sharing resources, and now in sort of more, their resources themselves may be distributed across multiple compute centers around the globe, right? So even if you have not that many quantum computers, if you can connect the calculations via a quantum network, you may be able to do a more intense calculation than you could before. Like all networks, their basic functionality is also to communicate information. In this case, rather than communicating zeros and ones, we're communicating, things like qubits. Okay, so now we're communicating quantum information. And of course, in some, I don't know how far distant future, build a true quantum internet. Okay. Just to give you a sense of some of the reality of some of these things. So I have here this quantum network in Madrid for quantum key distribution. And so you can see, you have like different, nodes connected by various quantum links of some kind. And so you can also get a sense of some of these distances, like 33 kilometers and so on. Okay, so to abstract that a little bit, so the main function of a quantum network. So we're trying to create, distribute, and manage these qubits and entanglements. And so we have sort of end nodes, which are very similar to the end nodes that you may be familiar with in traditional computer networks, right? It might be your, computer, it might be some other kind of device. We have repeaters that are going to, I'm going to say, quote, repeat that information. You can think of them they're almost, but not quite like routers in a computer network. Okay, because at this point, I'm not going to, so there's some similarity there. You may ask, why do we have everything connected? If I want to talk, if Alice wants to talk to Bob, why do we have these repeaters in between? Why do we have these repeaters in between? Why doesn't Alice just talk to Bob?
You lose the information.
Well, yeah, you're going to lose information. So I may not be able to send, a lot of, at a high rate to Bob if, he's like, I don't know, 1,000 kilometers away, but I may be able to send it at a high rate or higher rate if he's only 100 kilometers away. Of course, if I want to send to him when he is 1,000 kilometers away, I need something that will convey that information across multiple hops. Okay. Okay. So
I have a question. So
Yeah.
the difference between the quantum network and the normal network
Yes.
is just that the channels are basically allowing for quantum information to flow.
In some sense,
Okay,
yes.
okay.
And then, of course, things get a little weird because unlike a classical computer network, right, our bit error rates aren't necessarily as high, but also we can copy information. So like that leads, so for instance, like, you know, we can't make copies of qubits in the same way. And so that changes a little bit about how you have to think about protocol.
I see. Yeah, okay. Thank you.
Other questions? Okay.
I have just
Yeah.
one quick question. So we mentioned the repeater as a way to make up for signal attenuation.
Yeah.
What happens in the branching off points? Is that, because in the classical sense, one can just make copies. Is there a quantum analog of
So
that?
you could, yeah, I didn't show you like the full, like, so the internet is not this, right?
Mhm.
So, you know, this might be like a switch,
Mhm.
if you know what a switch is
Mhm.
in the traditional networking world, right? You might actually have proper routers, you know, directing traffic. But of course, they're still constrained by all the limitations that qubits and so on and quantum channels will have. So when I say this is not the internet, like the internet is a network of networks, which gives you this sort of hierarchy and a whole other set of things to deal with and addressing and all these kinds of things. People have started, like, if you know, on the internet, they talk about the network vertical stack. You heard of this? So where they basically have layered the functionality of what needs to happen so that like people can work at one layer without having to worry about what's happening at a different layer. And so people have also come up with like quantum protocol stack, network protocol stack as well. And that is still sort of, there's a lot of like active development on this kind of thing. Yeah. Okay. So our goal is sort of to communicate information from one end node to another end node. Okay. So in this sense, our goal is to communicate information, say represented by a quantum state psi, from one node out, another node Bob over a quantum channel. Okay. This runs into some issues. In a classical network, you might be like, okay, well, that bit of information I'm just going to convey along to Bob, right? One problem we run into is that this might be sort of precious information. Maybe we did a bunch of calculations, we got it. And the process of conveying this information to Bob could actually lose that information, right? And so there's some risk of that happening. And so we need to think about how to do that. So one way we're going to talk about is using entanglement. Okay. The other, another issue that we talked a little bit about is, well, Alice and Bob are really separated by a long distance, right? The rate of that we're going to get is going to decay exponentially, and so if we're only getting like 3 bits, you know, per second or something, that may not be sufficient for any useful applications. And so instead, we're going to shorten that distance and use multiple relays repeaters, for instance, to connect nodes. There is also there's no cloning theorem, right? So we can't do like just re-implement the algorithms we normally would in a classical network to sort of add redundancy and other things and make sure that information isn't lost or resend information. So like if Alice sends something out and somehow Bob can tell Alice, hey, you sent that, I never got it. In a classical network, Alice would say, that's fine, I'll just resend that information to you. Okay, you can do that. But one thing we can do is, even if we can't copy state, we can effectively move the state or into a different qubit. Okay. All right, so how we're going to transfer that state information. So if Alice and Bob are not too far away, and so let's say directly connected, we could just use teleportation, right? That I'll talk about in a minute. And then otherwise, we'll do what's called entanglement swapping across repeaters to get that information to Bob. Okay, this is gonna sound terrible, but it turns out we also need a classical channel to make this work. Because Bob will sometimes need to fix up state or know about what happened, and the only way you can know that is if some bits of information are sent over to classical channel to Bob. Okay. Okay. So so let me first talk about entanglement and then teleportation and then entanglement swapping. Okay, so I'm guessing you guys have seen this. Maybe. I feel like you guys probably know more than I do, but okay. But so two qubits are entangled, right? To generate a Bell state pair. So this is some maximally entangled pair of qubits. Okay, so if I measure one of them, right, it's going to collapse down, right, and they'll be at the same state. Okay, so where you have Alice and Bob. So remember, this is, let's say, the precious qubit we would like to transfer. Okay. And then to do this, we're going to generate this entangled, at least in the networking setting, we're calling this a link level entanglement and elementary entanglement. That has this C-pi state, right? This maximally entangled state. Okay. Okay. And then we'll have some messaging happening on the classical channel because generating this Bell state pair is probabilistic. Okay, so we need this before we can do anything, but it may or may not happen. And so what that means is we may need to wait a little bit, actually. Like we may have some information that's there that we want to send, but we can't actually send it just yet. We have to keep trying to generate this state first. Okay. Does that make sense, everyone? Okay. And of course, as we're waiting for this to get all set up, this qubit might also be like deteriorating, which is very different from the classical network setting, right? Like you're not like, if I don't send this message soon, my message is going to self-destruct, right? So that's not going to happen in the classical setting. But here we sort of have these, like, at least from my perspective, these are interesting decisions that have to be made based on like, oh, this thing is going to expire soon. Should I like go now, or which should I wait? Like, should I wait for higher fidelity entanglement? Like, what should I do? And there are a lot of interesting decisions that arise. Okay. But once we have that, right? So these two qubits, right at this point, once they're entangled, and of course they can be separated as far as we want once they're entangled at this point, right? They'll still be correlated. And once I have that entanglement, I can use it, the teleportation, to transfer this psi state. Right? So I wrote like this very high level summary of what is going to happen rather than trying to write out a bunch of math. So there'll be some interaction on Alice's end with psi plus, and then there'll be some measurements, and then there'll be some classical information that Bob needs to fix up his own state here so that it basically becomes the precious qubit that Alice wanted to transfer. Okay. So far, so good. Okay, that's all great. If we have Alice and Bob sort of connected by a shared channel. Okay. Oh yeah, that was my animation. I was very proud of that. So. Yeah. Okay. So, yeah, and this is what the bits to be fixed up. Just as a reminder, so what's happening here? So when we do this teleportation, we're going to consume this entangled pair. It's not going to survive. You get to see it again. Right. This isn't actually faster than light because until Bob gets those classical bits, he can't actually fix up his state to become P. Right. And so, and it really is a move, not a copy. We never at any point have like two copies of a P at any point in time because this Alice's qubit gets destroyed and then she sends classical information and then Bob fixes up the qubit. Okay. Okay. And I guess what we talk about in the networking world is multi-hop communication. So we're forwarding information across multiple hops. So in this case, we're back to having a repeater sitting in the middle. And we could have, of course, a whole string of repeaters. But here, what we're going to do, so we just saw having, we just talked about link level entanglements, right? Or elementary entanglements. So now what will happen is we'll generate a link level entanglement between Alice and the repeater, a separate link level entanglement between the repeater and Bob. And of course, if you remember, these things occur probabilistically. So there's a little bit of a coordination that has to happen. You're sort of waiting for different things to happen for all of this to actually go through, but we can ignore that for now. Okay. But now, if I could teleport this here, right? But we don't actually have an end-to-end connection between Alice and Bob. So what happens here? So there's what's called a Bell state measurement that can be done to basically swap entanglements so that this entanglement and this entanglement become this. So I think I call this B plus AR and B plus RB. We'll get this B plus AB entanglement.
In other words, this is before, so to speak, the quantum information.
We haven't done, right. So this is almost like an extra teleportation step that happens before we actually send this psi. Okay. So, and if we do this, and once we have that entanglement, so part of the reason why this is interesting is once we have it, it doesn't matter how far apart Alice and Bob are. So if we have like this chain of 100 repeaters, okay, that we sort of do this for. At the end, so the repeater actually doesn't learn anything about when we do the final, like, isn't part of this entanglement anymore. Okay? But once we've done it, they're still correlated as yeah.
The last step, the entanglement swap does it also require the classical channel?
Yes, it does.
Okay.
Yes, it does. Yeah,
because it should be only the interaction between the qubits in the middle, right? Which were not entangled before.
Yes. Yeah, I think.
But you need like classical channel.
Did I not? Hold on.
The one before.
Where did I?
So the one before this. Yeah.
Here. Oh, I didn't draw it.
Okay.
Yeah. But you mean?
So there's some interaction within the repeater qubits.
Yeah. Yeah.
And so the protocol, I guess, looks something like Alice and Bob, they have to send their particles to the repeater first. Okay, so now the repeater has these Alice and Bob particles, but
yes.
And then what? They make a measurement, but they're also sending classical information along the classical channel.
So basically, the classical. So there's two things. So there's one knowing something about whether it succeeded, and then also knowing how to fix things up.
Okay.
And so that is the main classical information that gets exchanged.
I see.
Yeah.
Okay. So when Alice sends the particle from Alice to the repeater, does she also send classical information at that point? Or it's only like
You mean
after?
here?
Yes.
Believe so.
Okay.
Yeah.
I see. The point is that you have a back and forth of.
There is a
classical
back and
information.
forth, so usually it's not that like. When we're sending that classical information, it's usually not very many bits. Like we may be saying like which bell state, like do you need to pick things that up to, which ends up being like 2 bits of information.
Right, I see.
But
Okay,
I'm also hiding the fact that this classical channel needs to be authenticated, which requires some more bits so that you can know that you're actually talking to certain, like, yeah,
authenticate meaning you're not talking to the wrong person.
you're not talking to the wrong person, yeah.
Yeah,
Like,
okay.
because otherwise you might think that like the repeater is Bob,
Ah,
and and so be like, yes, and then the repeater could then pretend to Bob to be Alice. And so if you don't know for sure you're talking to Bob.
but this is in an adversarial context, is the idea, or even just.
I mean,
There's
just like,
general uncertainty.
just in terms of cryptography, yeah, like, so like, you can drive keys, but there's usually some desired, you know, who you're, like, particularly in the case where you have these intermediate parties, like
Okay.
man in the middle kinds of things.
Okay,
I just
Yeah.
have one more.
Sure.
So, because the alternative to this would be to only teleportate this qubit that you have to the
Yes,
repeater and then
yes,
do this
yes.
consequently, right?
Yeah,
And because you
Yeah.
cannot copy this thing, wouldn't that be safe as well?
that would be safe. So actually there are 2 classes of protocols. Like one is called like prepare and measure kinds of
Right.
protocols.
Right.
Which I think is what you're more thinking of, and then there are like these entanglement swapping kinds of protocols. And since I'm more interested in the routing, I'm talking
No.
as well. But that's a great question, yeah. So I think maybe I was glossing over some of it, but.
you might expect the error to go exponentially though, you know.
You mean over this long?
You swap here, you swap here, you swap here,
Yeah.
I mean, small
Yeah.
errors accumulate.
Yes. So there's a whole post-processing phase
Uh-huh,
that
I
has
see,
to happen.
I see.
Yeah, but the one important bit though, in like, depending on how you do this, so like I'll talk a little bit, you can have a trusted node here, but that requires trust. If actually I should say even instead of it, like depending on how you do this, like prepare and measure, you may still have this entanglement swap, right? And you're still gonna have to deal with some kind of error correction. And what they call privacy amplification, but yeah. Okay. But once we have this, right, like once we have an entanglement with the party we want to talk to, we can then actually just teleport as before. As long as everything is set up, as long as we have sufficient fidelity, like, then things are okay. Okay. If you remember in the beginning, right, I talked about networks and having these alternate paths. Right? If you have multiple paths between Alice and Bob, you could be sending information on those paths sort of simultaneously, so that can also increase the rate. So there is some other benefits, and also if you have like an adversary trying to interfere with certain links, that can allow you to sort of route around those failures. Oh, sorry guys. This is actually quite powerful because the repeater, right? The repeater can actually be an adversary, right? The repeater could even be the one who generates the entanglement, right? Because if something is wrong, right, if there's going to generate something that's not this perfectly correlated state, it will be detected. And so this actually can be quite powerful. So that's just one other thing to think about. Okay. But I think this came up a little bit, is that there are a lot of places for failure, and the failure scenarios are not the same as in traditional networks. I mean, some of the techniques can be used once we're back to just bits, but others cannot. Okay. So now I tell you guys, well, I don't say another dirty secret, but like, So, for some of these networks, we don't really have repeaters that we've built that are doing all of this. So we're sort of using trusted nodes for some of this. And so in that case, the trusted node, for instance, if we have this entanglement, then the trusted node, then this side can be directly teleported to the trusted node, measured and forwarded on. Of course, this assumes that node really is trusted, right? Like think of it as if like when your information is traveling through the internet, like the routers are like, oh, look at your information. So which we don't really want. Okay. So that was just at sort of a high level, what a quantum network is, how information gets distributed. Okay, so what I wanted to do was talk a little bit about quantum key distribution. And then I was going to start with cryptography. How many people are familiar with cryptography at all? A little bit? Good. Okay, so this is just the art of hiding messages, right? Alice will have some key that she can use to encrypt a message, the ciphertext. Bob will use that key and his own algorithm to obtain back the original plain text. Okay. Of course, there is Eve, who can be listening in. And so if our encryption algorithm has operated properly, right, when Eve is looking at this channel, Eve should not be able to infer anything useful about this ciphertext, about the original plaintext. Okay. 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 Have you guys seen the Caesar cipher before? Okay, well, there used to be a cipher used a long time ago, and that was quite insecure. The reason it was insecure was that it was pretty easy to break because if you searched through all the keys, you could pretty easily find what was the right key to use. So many historical ciphers were later shown to be insecure, and even today we find algorithms that are insecure, and quantum brings other new insecurities to be found, basically. So in terms of security, what we mean by security is we're basically measuring it in terms of computational difficulty. So how long does it take us, right, to search through the possible keys? Okay, so for what we call symmetric encryption, where both Alice and Bob have the same key that they're using. Currently, we use sort of 128-bit keys. Okay, that's considered really good. Then you'll be secure. This is actually just a quick reminder because so in symmetric keys, the keys are the same, but the important bit here is that it requires you to distribute the keys. And so if it's just you and your friend who want to talk, that's really easy. If it's you and like a billion other people on the internet who want to talk, it's really hard to actually sort of coordinate in that way. So then we use public keys where the keys are mathematically related. It doesn't have a key distribution issue, but it's way, way, way slower. Okay. So in practice, what often happens is that public key is used to bootstrap the generation of a symmetric key. In terms of quantum computing, so, well, I guess things are now, we're finding new things that are insecure. So rather than the 128-bit keys, right, we say actually we're going to need 256-bit keys because Rover search, if we do brute force attack, it's operating in square root of n complexity, right? And so then we're sort of squaring the number of keys to get back the equivalent security in terms of computational search. Which this is quite a large number because there are 200 atoms in it. For public key, right, so those are relying, on this mathematical relationship between the public and the private key. Like for instance, Shor's algorithm in terms of factoring in efficient time. So a lot of this will break a lot of currently deployed public key algorithms, which is what you're using on the internet all the time when you're connecting to websites with HTTPS. So the solution, well, there are two solutions at the moment. One is basically to sort of fix this up. One of the things to fix this up is just use longer keys in the symmetric world. In the quantum, in the public, so for symmetric keys, use longer keys. For public keys, find other mathematical complex keys, right? So that would be what they call post-quantum cryptography. For quantum cryptography, use quantum resources in some way to derive the keys. Okay, so in the case of this key exchange, right, this quantum key distribution, that's actually distributing keys for the symmetric case. Okay. So that, just to keep in mind, like we're not trying to do public key there, we're just trying to get the two endpoints to have identical keys that they can use to do symmetric cryptography. Okay.
Can I?
Yeah.
So in light of that,
Yeah.
quantum key distribution is used like as a public,
Not as a public.
sorry, as like to generate a key to
Yeah.
then have symmetric
Yeah.
encryption. But at the end of the day, the communication would happen classically.
Yeah.
Using a secure symmetric key.
So, I mean, once you have the key, so it's interesting. So you could say, I guess it depends a little bit on what you're trying to do. I'm sure you could come up with other ways. Like in the case of quantum key distribution, you're distributing those keys, and then you're using that key to do some other, like you're basically deriving a sequence of zeros and ones.
Is the assumption that that's a symmetric key that I'm going to use?
That's your assumption.
So given that that's the case,
Yeah.
is the time it will take to exchange those original bits a little bit less important in the sense of like if I get my quantum key distribution algorithm to work in 1 hour versus 2 hours, of course it would be nice
So
to
it's
do this
actually,
as
it's
possible.
quite fast. I mean, so you can actually generate a fair number of bits.
Okay.
Like, although I don't know what like is, how it's going to scale to like 1 billion users or something like that. That's a separate question. But one, do I have this here? So one of the things that like, have you heard of like one-time pads?
Mhm.
So if you have a one-time pad, which basically you have as many bits as your message, right? Like you're perfectly secure. So if we're generating these keys, like if we're just doing it all the time in our quantum key distribution network that is like dedicated to that,
Mhm.
right? Like you can have like, you can almost generate like a one-time pad.
I see, okay.
In practice, I think I may talk about this somewhere. Oh yeah, here. So basically, ideally, like you just be like, I have my, and of course, if you're the military or something like this, these are things that are quite interesting to you, right? I have, then just generate, I have as many bits as I need to encrypt my messages. And of course, symmetric key is faster than public key. And so, in terms of encryption, and so everything seems good. In practice, what's going to happen is instead, so we said we needed 256-bit symmetric keys, a little bit secure. So as we're generating this long string of bits, we're chunking it up into 256-bit chunks. And then what we're doing is we're basically refreshing, like we're basically using that 256-bit key for a short amount of time, switching to the next one, switching to the next one, and so on. So that like, even if you get one of those keys, right, you're not getting all the everything. Okay. Oh yeah, and there actually are there are companies who have built like quantum key distribution systems at this point. There is hardware. Like from this perspective, it's like it's not vaporware. Like as people call it, like this is like quantum key distribution for production environments, right? Doesn't that sound really good? Like, long range up to 150 kilometers, higher key rate on short distances, like keys per hour. I actually don't know what 24 bytes. I don't know what that metric is. Decibel bytes? But decibel, maybe it's just decibels. Oh, maybe that's the rate. Yeah, maybe you're right. Yeah, I don't know. Anyway, complex network topologies. Are you guys not sold? Okay, sorry, moving on.
Are these companies mostly based, do you know, are these American companies, you know, or?
All around the
Oh.
world, yeah.
I was curious if there was like, there was just someplace.
There's a quantum arms race on at the moment.
Oh, okay.
Yeah.
Cool.
So, yeah. But, so just, so just to give you an example, so this is the operation. So we're not talking about quantum key distribution networks at the moment. We're just talking about quantum key distribution. And we're looking at entanglement-based protocols. So this is an entanglement-based protocol. There are others that are these measure protocols. And the other thing to keep in mind, so when I started, I said, well, in the network, we're going to use this entanglement to convey this precious qubit psi from Alice to Bob, right? In the quantum key distribution world, we just really need the entanglement. Because what we're trying to do is basically generate the sequence of Bell state pairs as entanglements, right? And then we measure them, we get the sequence of zeros and ones. Does that make sense? So right now, we're actually not talking about like conveying information of somebody else's qubit across the network. We're just saying, okay, generate a bunch of these pairs, and then have Alice and Bob each have one end of them. And then we're going to, Alice and Bob will independently choose a sequence of bases to measure the qubits that they have. Okay. And then over the classical channel again, they'll say, okay, what bases did you use? And then they'll only keep the bits that were measured in the same base. Okay. And then there's still other stuff to do to detect eavesdropping or disentanglement. Okay.
It's teleportation, right?
Yeah, basically. Yeah. Okay, so this just gives you a little bit of example. Like, so Alice and Bob, right? There's two bases they can measure, right? This is the Bell pair that was generated. But of course, you can rewrite, these and the other bases. And then if we do that, right, we can, so only if I'm in like Z, if both Alice and Bob measure in Z, will they both get 0, 1, and so on. Okay, so there's a little bit more detail here. Okay, so this is just giving you a sense of how they get the raw key. So they do this, they get a bunch of zeros and ones, a whole sequence of zeros and ones. I realize in this example, they're basically measuring in the same basis, right? So they measure, they get their sequence of zeros and ones. Even if they measured in the same basis, right, there might still be some error, right? So you may get a 1 versus a 0. So this is the raw key. We're going to call that the raw key that was generated. And so then what we want to do is start trying to fix up that sequence of zeros and ones that we got. And the first thing we need to do is just have a sense of what the noise of the channel is. And so one way that we can do that is if I choose a subset of my bits, and you choose a subset of the same subset of your bits, and we compare, and we say, do my bits match your bits? And the larger that subset of bits that we do, the more accurate our estimate of the channel noise will be. Okay. Of course, when we do that, we're both losing bits, and we're leaking information to Eve, the eavesdropper. Okay.
Excuse me, so
Yeah.
you say you're losing bits just because they become public, or?
Because they become, yeah.
Okay, I see.
Yeah, so if we're sending the information, because otherwise we then need another way to encrypt information that we're sending over.
Right, and
Yeah.
then it's the same
Yeah.
problem.
So,
I see.
okay. but if we know this noise, we can do some processing, some error correction, even. And so we'll end up with some corrected key. And I should have probably dropped some random bits, but I didn't, just so you could see things sort of shrinking. Okay. There's one more step though that happens. We're not like, okay, we're done, right? We have a corrected key at this point, but this whole process has leaked some information. Okay, Eve may be a little bit, based on the noise, based on like the percentage, like what proportion of we select each basis, may be able to infer something. And so then there's this final step that's called privacy implication that sort of hashes things down to this final secret key. And that's the symmetric key that will be used. Okay.
Could you elaborate a little bit? I'm not familiar with, so you now have the corrected key is longer, I guess.
It's shorter.
Well, I mean, going from the corrected to the secret, you're saying.
Yeah, it's gonna be short. I mean, it's sort of like as you're moving down, you're sort of losing things.
And how is privacy amplified exactly?
I don't know. I mean, there's the hashing maybe.
Is it possible for Eve to like dynamically alter the channel noise?
Yes, and actually, you know what they do? So, in practice, you can also yourself like, adjust sort of the strength of the signal to sort of combat Eve's behavior as well. Right, so you can imagine Eve doing all sorts of nasty things, but like in practice, right, so, these like decoy state, protocols and so on will do other things. Yeah, to be more clever, but I'm gonna ignore that for now. Any other questions? Okay. Just to give you, so assuming perfect error correction, right? So I'm showing here like the noise, amount of noise. This is like 0.02, it's going from 0 all the way to 0.12, and then the key rate. Okay. So the asymptotic key rate as noise increases, as you see, is sort of decreasing. Okay. And actually in this case, it doesn't actually take that much noise. So this is sort of the key rate function that will show up again later.
Is this like Q, like the fraction of those bits that you exchange that are wrong or something like that? And how is Q generated? What is Q then?
So I think it's a measure of the decoherence, like the probability of decoherence.
Okay.
Yeah.
Okay. Okay.
The rate at which things are going towards a mixed state.
So the y-axis is the success probability, right?
The y-axis,
Or is that-
yeah, like, I mean, because this is 0 and 1, so you can think of like, this is like the rate, the bits per second. Almost. Yeah, other questions?
No, it's like per channel use,
For channel use, so if I use my channel, what fraction of time will I,
generate
Gener-
probability.
yes. Yeah, okay. Okay, so this was just thinking about a single link in our network, right? Okay, so then we can say, well, what if we have a network, right? So what we have here, we have Alice and Bob. We have a bunch of repeaters, and then we have a trusted node here in the middle. Okay? So, so these, fiber optic channels connecting the nodes. And then you see these little dots, right? So those are going to be the memory, the quantum memory, holding a single qubit for each neighboring node. In our setup, we're assuming states decohere after one round of the QKD protocol. And then we're assuming everything is IID.
What is that?
Identically and independently distributed. So they all have the same, channel properties in terms of error and other things. and, and probability of entanglement success and so on. Okay. Okay, so, and then if you remember, we have a raw key, so after we just did our measurements in our, using our independently chosen bases, and then we have a secret key pool. So this is, after we've done all that post-processing, we've gotten down to bits that we believe are secure. Okay, so doing quantum key distribution in a network. So how does this operate? So this is sort of operating in rounds. So with some probability, we're able to create a link level entanglement with our neighbor. Okay, so those are these pink lines that are shown up. For some of these, you see we could have had a link, from here to here, but we don't. So it did not succeed. Okay. And then the networking person routing is sort of the thing I like, but so stage 2, we route entanglements by entanglement swapping. Okay. So basically I want to connect these link level entanglements into an end-to-end path between Alice and Bob. Okay. And actually what I'd like, if I can have multiple paths between Alice and Bob, that is good, right? Because that means I can have, some key rate over this path and another key rate over that path, and then I'll have, even more, keys create, even more bits created, basically. So far, so good. Okay. Okay, so when we're doing, once we have this path, right? What we basically have now is an end-to-end entanglement, one qubit held by Alice, one qubit held by Bob. You agree? Yeah.
And just to be clear, if you have multiple paths,
If you have multiple paths, you have a second qubit held by Alice, and with a second qubit held by Bob.
gotcha. Gotcha. So Alice and Bob, they have a whole store of them, and throughout this protocol, somehow they're able to determine whether some fraction of those bits were successfully entangled.
Yes, and whether they were successfully routed to Bob.
Good.
Okay, so even if these repeaters are controlled by some adversary, they can still
Determine if they were successful.
yes,
Okay.
and whether they were interfered with using some other.
Okay. Okay, cool.
Yeah. Okay. Okay, so we've done that, and so let's pretend. So now, once we've done that, we're going to look at what networking world is sort of called an overlay network. So we're going to build a more abstract network conceptually, thinking about just Alice, these trusted nodes, and Bob. Okay. If we didn't have those trusted nodes, we could just think about Alice and Bob, because Alice, the trusted nodes, and Bob are all the ones who actually have bits to work with, right? The actual keys. So this is the overlay network. Here we have 3 trusted nodes, T1, T2, T3. So in the next stage of this quantum key distribution in the network, what we're going to do is just then now attempt that entanglement protocol we talked about before, E91. Okay. And so suppose, and of course, depending on the underlying length of the path between Alice and Bob or trusted node, right, you're going to get, more, or fewer bits created, right? Yeah.
Is the probability of failure always independent of number of trusted nodes? Because I assume that you want more
Yeah.
trusted nodes for.
Because the trusted nodes are just they are basically acting as an end node.
Okay.
They're doing their own measurements. They've gotten the bits basically.
Mhm.
And so they're gonna do some, I will talk about in a minute, convey the keys on elsewhere, but they know the bits. They're not working with a qubit or entanglement that's going to decohere.
Right.
Yeah. So, okay.
And what's K in that equation?
K is the number of hops. Like, so,
Okay.
so if you, like, if you're thinking like Alice to T1, so suppose this is Alice and this is T1,
Mhm.
right? Then K is, I don't know, 1, 2, 3, 4.
Okay, right.
Okay. Okay, so suppose, this is a longer path, only 15 bits were generated, different numbers of bits were generated on each of these. Okay, now these keys, this is, when I say 100 bits here, this is 100 bits, some random string of zeros and ones that Alice and T1 know about. Okay, this is separately another 200 bits that T1 and T2 know about. Okay, we're not quite at like Alice and Bob have a string of bits that is their key. Right? We need to trust T1, T2, and T3 because they know our, information that's going into our keys. So the first thing is, because our goal is not really to set up keys between Alice and trusted nodes. We want keys between Alice and Bob. Okay? So here, Alice and Bob are directly connected. They have 15 bits of information they know, and only they know. Right? But here, this has 100 bits, this is 200 bits, this is 100 bits. In effect, we can only get 100 bits on this path. Right? So having more bits here isn't helpful. Right?
Mhm.
You believe that? Like we built up this capacity here, but like we don't have information that can, generate on this link. So this is what's called this final stage, that's key pushing. So basically, if you've seen like, flow problems in graphs or networking, this is like treated as a maximal, like a flow problem and just finding the maximal flow of key information between Alice and Bob. Okay.
May I ask,
Yeah.
the 15 bits you have directly from Alice to Bob, that's in the classical channel that they have? I mean, what do those 15 bits refer to?
Oh, so that refers to an end-to-end path from Alice to Bob
Mhm.
on which an end-to-end entanglement was established over which the quantum key distribution protocol was performed.
Okay, I see.
Yeah.
I see. So that's, in other words, that was a successful.
That was a successful, we didn't go through any intermediate node, an intermediate trusted node
I see.
to generate anything for that.
Mhm. This maybe, so the 15
Yeah.
bits is the size of the hashed key or something like that.
Yes, yeah,
Final
you
step.
could say the final, well, yeah, no, I think we could probably say that because at this point, we're gonna switch to classical channels.
Okay,
I was having a moment where I was like, well, hold on, maybe we have to do some more fixing up of things,
okay,
but I think, yeah,
thank you. Yeah.
okay. Let me just maybe wrap up, because this will give you at least a high level of everything. So at this point, so the question is how do we sort of do this keep pushing? Well, so what is gonna happen, so Alice, for instance, in T1, right? So I'm calling this key Alice T1 XORed with a key from T1 to T2, for instance. Okay. If I do this, so if T1, who knows the keys here and the keys here, so knows this key and this key, and I take that XOR, then if T2 XORs with this,
Mhm.
they'll get back that.
Mhm.
You believe that?
Mhm.
Okay. So if we just sort of do that, eventually Bob will have the 100 bits that were the key here. And it's okay to send this information over a classical channel because these, bits that we derived are basically random bits. So they're basically operating as a one-time path, okay, which is about as secure as we can get. We're also assuming that the adversary can observe but not interfere with the classical channel. So if the adversary was just like blocking everything, then we can't really do anything.
But you're saying that they can eavesdrop and they'll know, but aren't you saying they'll know the key that is then being
They
shared?
won't know the key because so the quantum channel, we're assuming they could actually interfere, which we could detect. The classical channel, they can observe everything.
Mhm.
and they can observe us sending this, right? But if this is essentially a random string, in fact, it's a wonderful key, right? That's exactly all the work we did. So if we use this to encrypt this, right, then we're basically using like a one-time pad or something to encrypt this. And so there's, even if they observe, if we did everything correctly, they should not be able to actually.
But if they observed all of the exchanges.
Even if they observe all of them, right? Because then we'll get another one-time pad here. Because they don't actually know, they're never observing the keys themselves were created over the quantum channel. Right? We're only ever sending these XORed keys.
Okay. Okay.
So if they had, like, if they knew, you could imagine, like, if they knew one of these, that things could start leaking
I
information.
see. You're saying that the Eve does not have access to Alice and Bob's key in particular, so they can't undo all of the XORing properly. It will look like
Yeah.
randomness.
Yeah, so they'll,
Okay.
right, they won't be able
I
to say,
see.
oh, I see when you encrypt that, like, if I
Yes.
knew that, like, you know, like, you're encrypting AA or something.
I see. I see.
Yeah.
Okay, thank you.
Okay. So let me, okay, I'm just gonna maybe wrap up with the last slide here, and that way I don't go over too far. So you can imagine, actually, there are interesting routing problems that start to appear, right? Basically, particularly because you have this aspect of like, well, you know, this entanglement's going to go away on this link, but not that link. You know, what's the fidelity of these different things? If you have larger, quantum memories, then you might have a bunch of qubits sitting in memory that you could create entanglements with, and so on. There's a bunch of interesting decision making. Just something to keep in mind is that, like, certainly as paths become longer, you're getting like larger and larger bit error rates. And if your end-to-end entanglement isn't of sufficient fidelity, actually none of this is that useful. So, okay, let me, so we made it through the first, I'm just gonna skip to the end and then we can wrap up here. So maybe just as a few takeaways, like, so quantum networks, are sort of a stepping stone, albeit maybe an early stepping stone to the quantum internet. There are currently real-world deployments of quantum networks and QKD. And they're all actually real-world, applications, or QKD and this distributed computing. At least for me, there are lots of interesting decisions that can be made, which is interesting for me from like sort of learning how to make good decisions in these kinds of environments. Okay, that is it. I'm happy to answer more questions.
So if I can say something,
Yeah.
we're on time, so if anyone wants to leave, that's totally fine.
Yeah.
I would just, because we bombarded you with questions
Yeah.
all throughout, I was wondering maybe there's either 1, 2, 3 slides that you would like to highlight.
Oh yeah,
That's
let
good.
me show you. Can I?
Yeah, of course,
Okay.
because we have so many questions, I think it's only fair. to
I
have to-
don't want to keep people.
Of course.
You mean from the last section?
Yes. so
Yeah.
maybe
Okay,
some
let
key
me talk a
things
little
that you
bit
want
about
to-
this. So in this work, we sort of looked at two things. One was, so like you saw here, okay, well, I could set up these routes, and different lengths will give me sort of different, fidelity within, and then entanglement. But you can imagine, right, when the network, like, you may not be able to choose the topology of your network, right? You may, if you're reusing existing optical infrastructure or so on. So you may start getting asymmetries, for instance, in how things are distributed. And this is, I guess I should say, this is in the context where we have both repeaters and trusted nodes. Okay, so, in the case, as you're seeing with the trusted nodes, they have to be trusted, but they do reduce, error, because they're basically measuring and being like, I've got my bits, and now I can forward them on without having, to worry about certain things. Okay. So we looked at having a combination, and so that gave us sort of, if you're willing to have a few trusted nodes, that actually gives you a big performance improvement. So in that context, though, like depending on where those trusted nodes are placed, you may get some kind of asymmetry in the network. Okay, which then starts to mean actually how you do routing. You may want to change that. And so this is, we have sort of this dynamic, like sort of dynamically choosing the paths to route those entanglements to Bob, for instance, to sort of maximize the key rates that you're getting. When you start doing this dynamic entanglement routing, right, you may end up with longer paths, sort of with more diversity in like the key rates along those paths. Okay, so when you do that, you actually need to be, if you have longer paths, you're getting, smaller key rates, but if you have more multiple paths, you may actually be getting better key rates. And so there's some post-processing that you can do to actually do better overall, right? And so one of the things that we do is, so for, with the, like, if you sort of segment the key pools, sort of depending on their error rates. Like if you say, I'm going to do the post-processing for this key pool separately from that key pool because they have very different error rates, right? That can actually improve your total key rate versus not doing that. So that is one of the things that we, is what we call the key pool segmenting. And then we just, do this couple of damage distillation. This actually just gives you a little bit. So when I talked about, what the trusted nodes we're doing, I sort of glossed over it, but actually now that you've seen the key pushing and QKD, this actually may make more sense. So basically they're doing exactly the same thing. We derived this key for this link. And then if I derive sort of the key for this link, but then if I XOR these two keys together, then Bob will have the original AT key. And then just actually, okay, so I can show you a result. Okay, so in this, here's our network with Alice, the trusted node, and Bob. And then we have some results here, the decoherence rate on the x-axis and the key rate on the y-axis. And then we're showing a comparison of strategies. So the red is just static routing, where like you've decided your routes, you're using the shortest route paths because that gives you the highest fidelity. And so that, so you're just going to focus on that. But actually, and then this purple is actually if you have no trusted nodes in the network, right? And then this black line is using the dynamic routing. And then this blue line is in the ideal case where you have one trusted node. So you can actually do a fair bit better. Let me just see. This is just a little bit about the issues. Like basically, if you're the static routing will be like, I'm going to maximize the key rate between the shortest pairs. But actually that is because, because then what happens is some of the overlay links will have a higher key rate, but the others will have a much lower key rate. But that's problematic because really it's the lowest key rate that you're going to be able to push through the network. Okay. Then this just gives you a little bit of a sense of the key pool segmenting. So you can think of this is just the error from this is sort of a multi-hop polarizing channel. So this is K is the number of hops in the path again. And so you can think of this is telling us something about like, the error depending on like with what probability we stay in the original state versus we end up in a completely mixed state. But the thing is, this is why the key pool segmenting matters, is that if we have paths of different lengths, right, we'll have different amounts of noise. And so so we'd like to reduce that if we can. And so if we just say instead, okay, we're going to process, basically key pools based on the amount of noise together, right? Then that will actually give us an overall higher key rate. So this actually, so for instance, this just gives you an example here. Like the blue line is if we don't do this keepable segmenting, and the gold is if we do, and the x-axis is again the occurrence probabilities, and the y-axis again the key rate. So and this is actually in the case of the dynamic routing, it's actually quite useful because we're getting longer, noisier paths. So we can sort of separate, you know, the keepables based on their noise is actually quite helpful. This is just classical advantage distillation, so I'll skip that. Although it does, so having it combined with the keepable segmenting actually gives better results than just having them alone. And then it's also helpful for the dynamic strategy. Okay, and this is my last real slide anyway. So then we actually, so I think the previous slides I was showing things on these sort of grid topologies. This is actually looking at random geometric graphs and then comparing like the dynamic routing with everything with static routing and seeing how the performance was. Yeah. Okay.
When you say random graph, do you mean like Erdős-Renyi random graphs or?
It's a random geometric graph, which means that if I place nodes randomly in the plane and I look, you know, to see and give myself a radius around the nodes, I connect nodes that are within a certain radius.
Do you find that the network topology has a lot to say about the success of the algorithm, the dynamic or static?
Well, so what it does say, so depending on like we looked at, so depending on the density of nodes, right, or conversely their radius, right, you'll get more or less well-connected graphs, right? Let's see here. So let me just here. So if you see these R's, these were the so I think the higher values of R, right, are going to be the more well-connected random graphs. So, and then we are also varying the capital R's here. These are like the probability that your Bell state measurement succeeds. And then this is the basically, you know, your link entanglement generation succeeds. And so let me see if there's something interesting else that I can tell you guys here. So one thing to observe, for instance, is that in this case, we have a, you know, Bell state measurement succeeds with high probability. Or for instance, here, Bell state measurement succeeds with high probability, low error rate. It doesn't really matter what you do, right? Like it's like you don't actually need this, right? Because your network is actually quite high quality, right? In this setting, right? So you can see, and of course the key rate is also higher in this setting, right? In this setting, we have, right, you know, a lower success probability, right? And so on. So we're, you know, in the case, let's see here. These are 0.3, 0.2. You can see this is solid. Oops, sorry, I think these are needing to be fixed. But this solid line is the dynamic routing. This dashed blue is a static setting, right? And this R is telling you that it's a denser graph, right? And then this purple is sort of if you have no trusted nodes, okay? And so here you see, right, like, okay, well, if it's denser, we're doing better than the static with a bigger gap, right? Here with the green lines, right, we have a less dense random geometric graph. The solid green is the dynamic, and the dashed green is the static. And so you're getting a little bit, there's a little bit. Which is, this sort of makes sense, right? Because if you're in a denser graph, you have more alternate paths. If you're in a sparser graph, you don't. And so like you can't really take advantage of dynamically routing if you don't actually have paths.
So,
Yeah.
so an obvious question for
Yeah.
folks in the network science world, that these like scale-free networks would be potentially ideal for this kind of thing.
Well, the thing is, okay, yes, but the problem, right? Like if you're thinking of how you connect things in the real world, like you're thinking of how you connect networks. Like if I can just put links over you to somebody else, that would be great. But in practice,
It
like
doesn't exist.
I have to go through you to get something somewhere else.
Right, so the random geometric graph is a good model.
The random geometric is sort of a more realistic model for a lot of this.
Okay, cool.
Yeah, particularly for these kinds of networks. Yeah.
What sort of algorithms do you use to construct a dynamic network? Like, is it like this looks like an optimization problem because you want to sort of maximize
You mean a dynamic network, you mean a random geometric graph network?
the one you're kind of using here.
Oh, okay, so we're using random geometric graph. This is a dynamic routing strategy.
Right.
Yeah,
So it's not like a max cut problem or anything. It's just a normal.
it's just yeah, actually, the reason why I'm like dynamic networks, I actually think about dynamic graphs, but in other contexts, I'm like, oh, there's a dynamic graph I didn't see here. But okay, no, that's not, yeah. Yeah,
So I have a general question.
sure.
Quantum communication.
Yeah,
So obviously entanglement was referenced a ton in this presentation.
yeah.
So is the current standard in the commercial settings or what people are doing in research, is it just basic entanglement, 1 degree of freedom? Or are we talking about, do we ever get to hyper entanglement where we have multiple
Oh,
degrees
yeah,
of freedom?
like we're, sorry, maybe like where you have like more than 2 qubits, is this what you're thinking? Are you thinking of something?
So, I mean, I'll preface this by saying I'm not a quantum person.
Well, I'm not a quantum
Sure,
person
okay.
either, so we
There you
talk
go.
all day about things we don't know.
There you go. But my understanding of hyperentanglement is
Yeah.
you can have 2 photons.
Yeah.
And photons have many degrees of freedom,
Oh,
wavelength,
I
polarization,
see,
etc.
I see.
So hyperentanglement would be you're entangled, for example, in both wavelength across these photons and polarization
Oh,
across
I
these
see.
photons. And so my expectation is maybe that would increase the capacity of information.
That would be really interesting actually to think about. I mean, it's a little like, well, given that I don't know anything, I don't know that what I'm gonna say is a good idea. But like it does feel a little bit disappointing, even though I'm telling you guys about this, that like we have these qubits that can represent so much more state. And then they just collapse down to like a 0, 1 bit, and we're like, and here we go, like just encrypt as we always do, and somehow, like, and maybe somebody is looking at how to, I don't know, because it's like we're using it. Yeah, like basically to get back to the classical world, and that somehow feels disappointing, even though I'm like, oh, we get to route, like, but there is one other, like you can have more than 2 qubits entangled together, right? And so that can let you have like multi-party kind of communication in a sense, or like generating like keys for multiple users in a group of some kind. Yeah, or like a broadcast group or something, or like, yeah.
Just sounds good. I was wondering if anyone's tried implementing the entanglement swapping algorithm.
Oh, well, as far as I know, there are no commercial repeaters. So as far as I know, nobody has built repeaters. I don't know. I don't actually
Not
know.
commercially, I mean, even like in
I don't know.
lab setting.
I don't know. Like I've been told there are no repeaters.
Okay.
But, yeah.
It's a very active field of research.
No, because teleportation, for example,
Yeah.
is more than 50 or maybe even 50 years ago that it
Yeah.
was implemented.
Yeah, I don't know why. Like, I don't know. I don't have enough of understanding of like what's happening below to know like what is the fundamental limitation, right?
Okay.
Or maybe it may just be like, you know, at least in the commercial world, they're going for like what's giving them money now, right? And so, and then the case of like, you know, I mean, I don't know what the US government has done. Like, I don't know, but like, yeah.
So those commercial, to follow up, those commercial applications, I mean, they're not able to use repeaters. What exactly are they selling?
I mean,
Do
so
know?
you can still, right, you can still build some kind of network, right? You can use trusted nodes.
These trusted nodes, these
Yeah.
elementary links that you're calling.
Exactly, yeah, like you can still, it's just, you have to trust your node,
Uh-huh,
which is like,
interesting.
yeah, is the limitation. Yeah.
Thank you. I think if there's any more questions, I think we'll wrap up.